Alright, this video will be an introduction to the our second lab in the software and system security class, which is the Buffer Overflow lab. So this lab is adopted from the seed lab. So in this video, I'm going to introduce specifically the task 3 to task 6, which is the 4 levels of the Buffer Overflow experiment. And if you are using Windows machine or the X86 architecture machine, you should refer to this video and look for the instructions and also some of the small hints on how you are going to work on your experiments. And also you want to make sure that all of these values, for example the memory addresses shown in this video, will be different from what you will see on your own computer. So you just learn from how to work on it, but you are not going to directly copy the value, because copying value will not work on your own computer. So the first thing is we're going to enter into the provided lab setup folder, and I have renamed it to the overflow because I want to show it like a shorter prefix here. So on your machine, just like navigating into the code, and you will be able to see using the cd change directory into the code in your terminal. And the first thing you want to make clean, although there will be nothing here inside your starter code, but you can always do the make clean to clean everything inside this for the previously compiled files. And there will be a small change required for you to make inside the make file. So basically you can double click into the make file, and previously there should be some other. So there will be a longer target here, so it will also include the stack L1 dbg to the stack L4 dbg. So you are going to remove all the other targets, only remains the stack L1 to stack L4 as the target, and you keep everything else the same. Otherwise you will face some of the problems when you are doing the debug for the stack L4 for our level 4 program. Alright, so let's first start with the first task. So the first task here will be the level 1 task, will be in a scenario that you know the buffer size and it is on a 32-bit program. And we already know that the buffer size is 100 byte. So to do this, so we are going to first create a bed file. We are going to create an empty bed file, and we run the GNU debugger. Oh, and we have to compile all of our stack L1 to L4. So we use make, and then you have to input the passcode for your account. So because you are going to change some of these stack files to some of these binaries to root owned setuid program. For example, here you can see all of this red background showing that all this stack L1 to L4 are root owned setuid program. And by executing those programs, you will be able to enter into the root shell, which is the Z shell. And you also need to turn off the countermeasures if you haven't done before. So basically, we have we have 2 universal countermeasures have to be turned off, and the others are related to this binary file wise. So you first have to turn off the first countermeasure, the ASLR, which is the address space randomization. And then you also need to link the Z shell to the shell, which means that you are going to create a symbolic link. In this case, whenever you are executing the binary shell, it will be linked to the Z shell, because this Z shell is not the protected shell. It can directly run as the inside the root UID process, as I mentioned. So, and if you do not have the Z shell, for example, you want to first check whether you really have the Z shell or not. So by doing this, you can using the command file binary Z shell. So if there are any of the output here showing for example, this is a 64-bit LSB shared object or whatever, so if you can see some reading like this, means that you already have the Z shell installed. Otherwise, you need to install the Z shell using the apt command. So this is the command if you do not have the Z shell installed in your system. Otherwise, when you are creating a symbolic link, it will going to show you and then after you can still create the symbolic link, but when you are executing your stack program, it will going to give you an error because this Z shell does not exist. All right, so these are the preparations. So now we can see we're going to back to we have created the empty bed file. And the first thing we need to do is the GNU debugger. So we do gdb stack L1. So remember that here we are going to using the dbg binary specifically for the debugging, and we're using the stack L1 for the real attack. Then because in the debugger we're setting up some of the flags. So basically in this case you can like using this empty bed file to see how are the programs are really executing. So you are going to debug the dbg file. And this is the reason why we are removing those entries in the flags in the make file, because so there are accidentally some of the errors when we're creating them, and if you are not using this updated make file, you will get having problem when you're working on the L4. So in the when executing the L1 dbg in the debugger, you're going to first refer to the command here in the X86. So in the task 3 5.1.1, so you are going to create a breakpoint at the BOF function, which is our vulnerable function. And then after creating the breakpoint, you are going to run the program. And at this step, the program or the instruction pointer has just entering in the BOF function, the BOF function, and you have to do the next. So the BOF function will be able to reach to the string copy, which is the command that we are interested with. So this command is actually the vulnerable command that will cause the overflow. And at this moment, you are going to check the address of the EBP pointer and also the buffer address. So here is the address for our EBP pointer, and we also need to check the buffer address and calculate the offset. So now we have our EBP pointer address and our buffer address. So the next step will be we are going to changing our exploit.python. So this is the file we are going to generate the payload. So there are something we have to change in the very beginning. So in the very beginning here, we can see here is a if and else condition. So for the if, so the first part of this if is that so it will going to execute when you are using the macOS system, which is using this ARM architecture. And in the X86 architecture, the shellcode for 32-bit and for 62-bit are actually different. So you will need to refer inside the shellcode, inside the call shellcode.c program. You are going to refer here and copy the correct version of the shellcode into your exploit Python. So here we are working on a 32-bit machine. So we are using this version of the shellcode. So this is for the 32-bit machine. And we copied here, replaced what originally here should be a series of the no-ops, that's the X90. So we replaced it here. So this is the first thing we have to change for the 32-bit machine. And then we are going to calculate our offset. So before that, we first look at how the payload are sized. So basically we have 517 byte. So this is the size of our payload. So this one does not change. We're using the 517 continuously for all 4 levels. So what have to be changed is mainly in the below. So we have to change the start and the return address and the offset, and also here the arrow. So this arrow means that this requires how the stacks are aligned with in different bits of system. For example, for the 32-bit machine, we have to change it to 4 because this is how the 32-bit machine are aligning their stack, like 4 bytes per step. So we have to change this to 4, and then we're going to calculate, starting from calculating the offset. So for the offset, this is the distance between the buffer start and the place where we place the place we are going to place our return address. So this will be referred to the EBP pointer. For example, here we have the EBP pointer at CB28, and we also have the buffer at CABC. So you can using this hex calculator to calculate the distance between them. For example, let's directly do okay, this 66C, so this is a hex number. We convert it to decimal, so we can see 108 bytes. This is the distance between the buffer and the EBP pointer. And we already know that, so in the 32-bit machine, the return address is 4 bytes higher than the EBP pointer. So which means that the offset here between the return address and the buffer will be 112. So we first replace this number to 112. Always again, as I mentioned, you have to read from your own values, not from directly copying from here. So you have to read from your value, calculate your number, and put that inside all of these numbers inside the exploit Python file. All right, so we first calculate the offset. So this is the place we place the return address, and this will not change. And then the next step is the next step is where we place our bed file. So where we place our shellcode. So if you still remember in the class, I mentioned that so for 32-bit machine, you can place the shellcode at the very end of this at the very end of our payload, and this will give us the no-op sled in between the return address and the shellcode. So in this case, for example, we have 517 bytes of this of the payload, and we have 27 bytes of our shellcode. So you can easily calculate if you want to place the shellcode at the very end of the payload, you are going to using 517 minus 27. So the offset here, so the start here can be replaced as 517 minus 27, which equals to 490. So this is the highest offset you can get if you want to place the whole shellcode inside your payload. And any number lower than 490, for example, we can do 470 or whatever. So any number lower than 490 will be okay. But you also have to remember it cannot be significantly lower. For example, it cannot be lower than 112 or actually 116. Otherwise, you will not have enough space to place your no-op sled. So in this case, we having a no-op sled in between the offset 116 after you have put the return address and the 490. So all of these are for the no-op sled. And whenever the return address are returning to any of this no-op sled, it will eventually guide to the start point of our shellcode. So the next step will be what should be the value to be put inside this return address. So let's see how we calculate them. So we're having this CABC. So this is our buffer address. You remember this? And this is our EBP, which is 4 bytes off higher than EBP, which is our return address. And in the 32-bit machine, we place the no-op sled higher than the EBP, which means like 116 bytes higher than the buffer. So basically, by doing this, we can directly place, for example, using the CABC, plus we can do plus, for example, we can plus 100. So yeah, if we plus 116 here, so this is the minimum value that will work in the GDB, in the debugger. And if you still remember, in the debugger, the stack or the buffer is actually lower than the real execution, because when the operating system calling the debugger and when they call the function, they will push extra parameters into the stack. So which means in the real execution, this value, this 116 should be higher, which means that you are assuming all of the memory address are moved higher. So basically here, my assumption is that, so we can first, for example, we can place 160 as the offset. And this is the decimal value. When calculating into this into the hex memory address, it actually equals to CBBC. So let's see if this works. All right. So we first quit the debugger, and then we create the. Let's go back to the code, and let's first run a Python to create the payload. And you can see bed file created 517 bytes. And the shellcode is 27 bytes at offset 490. So now let's try to run the stack program to see if we can get a root shell. So it works. So which means that so currently this 160 bytes of the offset is we are very lucky. We just directly landed into the no-op sled. So this is our first case. And so this concludes your first level. And when you are working on that, just remember to calculate the offset by yourself. And you can also try some other numbers of the offset, so they are all will be fine to see like they will be giving you different outputs. And then let's see the second level, level 2. So for the level 2, here is actually comparing with the level 1, which is we know the buffer size is 100 bytes. For the level 2 here, the problem is that we do not know the buffer size. So it can range between 100 to 200 bytes. So which means that in the, basically here you can see, once we get this pound sign, means that we are getting into a root shell. So you can see the effective user ID here equals to 0. So let's see So let's see how we can do the level 2. So the first step is still like we're going to remove the old bad file because we want to using the empty one to do the debugging. And we directly execute. And all the operations are the same. We need to get the we need to set the breakpoint, and we also need to get some of the address. For example, here we still set the breakpoint as our vulnerable function, and then because we do not know the buffer size, so actually here you should not using this GDB to get the address of your EBP pointer, because in that case you will be able to calculate how large the buffer is. So now we only get the value of this buffer, so we just know where the buffer starts. So basically we're going to do run next buffer. So now we can see the buffer address is at CA80. So this is the new buffer address with the unknown buffer size. So what should we do on the exploit? So basically here, so something could be changed and something does not have to be changed. For example, here is still in the 32-bit machine, and we do not need to change the shellcode, and we also do not need to change the start, because here we can still put the shellcode at the end of our payload. So the only thing we want to change is actually the offset and also the return address. So we first take a look on the offset. So in the class I have mentioned, if you are facing with a unknown buffer size, instead place a return address in a specific location. So in this case, we are going to do a technique called spraying, which means that so instead of place one single return address, you have to using a for loop to place multiple bad files, to place multiple return address in a specific area. So let's see how we can using this you are going to write these for loops by yourself. All right. So this can just like you are going to add a for loop and setting the starting point and the end point, and also the step size, because this is like 32-bit machine. The 4 bytes is the size. So in the first level, we having this buffer size as 100, and we have the offset as 112, which means that we have a small like a gap in between the buffer and the EBP, and this gap may change or may not. So in the case of like 200 bytes in the case of 200 byte of the buffer size, we can do 224 for sure, but there is no harm to make it larger. For example, here we can do 256. And you can make it even larger, for example, reaching like 300 or even higher. But remember, the larger you spray the return address area, the smaller the no ops that you will get. So in this case, it's just like a balancing. So we just select the 256, and in this case, this value will not be used. But we can keep it here, but we just don't use it. And now, how we are going to change the return address? So in the previous level, we're taking the 160 bytes of the address higher than the previous buffer, and now in this case, we have the CA80 as our second buffer, and if you compare with the previous one, CABC, so the second buffer in the GDB is actually lower than the first buffer. So in this case, we can first try if it works. If we directly using the CA80 plus 160, which means like changing it to CB80, okay? And we directly quit the debugger and create the bad file again. So in this case, you can see we got a segmentation fault. So here are actually different level types of this error message will be reported from the terminal. So the segmentation fault will be the most common one you've seen. So this can mean to different types of the errors. So in most of the cases, when you get a segmentation fault, it means that the return address, so this address is actually pointing to somewhere not the no-ops let. So it can be a memory address which cannot be executed, or it can be even directly outside your whole stack. So now let's see what should we change here. So we know that this CB80 is actually 160 bytes higher than the CA80, and because we have a larger buffer, so the buffer is actually moving lower than the first lab. However, the changes here is that in the previous lab, we only have one return address put inside the payload. And now we have like around 144 bytes of the 144 bytes of the return address sprayed on the payload, which means that so in this case the no op sled is even higher than the previous lab in the previous level. So in this case, for example, we are going, if we still put the CB80 like 160 bytes higher than the original buffer, so this will lead you to another return address, which means that the return address will return to the spraying area. And this is not a legal instruction, so this will give you a segmentation fault. So in this case, we are going to change it. So we are going to make the CB80 slightly higher. So let's try different values. For example, we increase this to another. So we can use in smaller steps. For example, we can do 80, we change it to CB80. So let's see if this works in this time. Still segmentation fault. So let's change it a little bit more bigger. Still. And then let's change it even higher to, for example, E0. And we got the shell. So you can see here, let's see the offset changes, how the offset changes. You can using this hex calculator. So now we have the CBE0 minus our buffer inside this the original buffer in the debugger, which is the CA80. It's 160. So in this case, we can do. So in this case, you can see this is 160 in the hex, which means that in the decimal, it's 352 bytes higher than the original, than our level 1. So you can have some insight. So basically here, when changing from level 1 to level 2, so you first are going to spray the buffer using a for loop, spray the payload using a for loop, and then you are also going to make multiple try on this new return address. And the intuit, or the the basic direction is that, so although the buffer moves lower due to the larger buffer space, but since you are having a larger sprayed area for the return address, so you are going to change the return address to somewhere higher than your level 1 experiment. So again, let's see. So here we can see the EUID equal to 0. So this is a root shell, and we can exit and move to the third level. So in the third level on the X86 machine, so now we are going to work on a 64-bit program. And for the 64-bit program, so we have to make some significant changes. We can make some significant changes, and this is actually very important. So you should first read through all of these challenges, and also read through all the challenges, and you will be able to see that. So for example, here the biggest problem with the 64-bit machine is actually you will always have some binary zeros in each of your memory address. So which means that so the string copy will stop when they see the binary 0. So we have to say that for multiple times. And this is actually very important, and this is what we're going to guide the overall construction of your payload. So for example here, let's just first do the experiment, and I'm going to show you how you're going to change the payload. So we first remove the old bad file, just as before, and we create a new one. And then you are going to do the debugger for the stack L3. And now we have some more changes. So in this case, the first change is that so in the 64-bit machine, the name for the register have changed. So in the 32-bit machine, we are using the EBP pointer, right? So in the 64-bit, so the pointer or the pointer has been renamed to RBP. So this is what we're going to do. So we first set the BOF for the breakpoint, and then we run everything the same. We do next, and now we are going to get the address for the RBP pointer. So we do, and then we also get the buffer name hasn't changed; it's still named the buffer. So we got these two different addresses. So the first D960, this is for the frame pointer, and we have the D890, so this is the buffer address. And then we can calculate their offset. So again, using this hex calculation, D0, so this equals to 208 bytes in decimal. And another difference here in the 64-bit is that, so in the 32-bit machine, so the stack are aligned as a 4-byte step. And here in the 64-bit machine, the stacks are aligned at 8-byte step, which means that so when the RBP pointer are pointing to 208 bytes higher than the buffer, the return address will be located at 8 bytes higher than the RBP, which means that we can first get our offset here is 216. And also remember, so in this case, you are not going to do any of the spray because again, as I mentioned, the spray will cause the string copy to stop at the very first return address. So we're going to change back to our like single line of this single line of the return address. And another thing, because the step size has changed, we also need to change this elf equals to 4, change it to 8 because now we're in a 64-bit machine. And now we are going to work with the offset and the start value. Oh, and also we have to change the shellcode as well. So refer back to the call shellcode.c and copy this X86 shellcode back to your program. So now, instead of the 27-byte 32-bit shellcode, we have this 30-byte shellcode here. And this will give you some of the insight, so where to put the content. So now, the problem is that, so here we having this 216. This is the place we place our return address, and the return address should be the last thing that we can copy into the buffer. So which means that we have to place the shellcode before the return address. So we all know that the return address will be covering the area, so we have the 8-byte return address. So the payload will be length. So length of the payload now will be the valid payload will be 224 bytes. And we want to place the 30-byte shellcode below the return address. So the easiest way is that we can do 216 minus 30 as our start point. So we can do 186. So this can be the offset for our shellcode, right? And then we are going to, because here we have some differences, so we are going to show you the so I'm going to show you the experiment on the debugger and to show you where could be the problem happens. So now we can make it a little bit simple. So now the return address, we're not going to consider the offset between using or without using the debugger. We can directly using this address in from the debugger. So let's, for example, let's see, we have the buffer start from 890, and the biggest, and also we have the shellcode starting from 186. So this is actually between the 186 and so the 186 bytes higher than the 890 is the space we can place our no op sled, which is like we can land our return address. So let's calculate this first. So first we calculate the 186 into decimal 186 equal to BA in hex. So what are the space we can place our no op sled? So we can do D890 plus. So this is the higher bound that we can place that our return address can return to, because in between D890 to D948, so in this area, this 186 bytes are the place we can use for our no op sled. So this is actually, by doing this, we can maximize our no op sled, and let's directly select one random value in between here. For example, we do so we can do like 30 bytes, 20 bytes, 32 bytes higher. We can do 32 bytes higher than the start of the buffer, of the GDB buffer. All right, so let's first see how this works inside the debugger, and this will going to give you a very interesting result. So we first quit the debugger, and then we create a bed file. And now we debug the original. We debug the stack L3 program instead of debug the debugger program. All right. And then we do not need to set any of this. We do not need to set any of the breakpoints. We just want to see how or if the program can execute. So now, if everything works correctly, if our assumption is correct, so in this case, you will be able to get a normal code, not a normal shell, not a root shell, because this is running inside the debugger. The debugger is not a set UID. So let's see what happens. You are going to see something like this. So you are going to see a error message here. So you can see the error message shows you like the error message why it's so let's first all right, back to the level 3. So I have made some changes. So previously I'm setting like using this D8 maybe A0, right? And we are receiving this type of address. So this address is different. So what we want to show you that, so this address is because that we haven't correctly landed into the no-ops lat. And once we make it a little bit bigger, for example, we set to D8A0. So in this case, once we have created the bad file and using D8A0, when we are using D8D0, which is like, let's see, D8D0 minus D890. When we do 64-bit higher, when we do 64 bytes higher than the buffer address, we will be able to successfully land into the no-ops lat and then executing the executing the shellcode. However, in this case, we cannot successfully execute the shellcode, and you can see here for the memory address, this will give you a very interesting result. So for the D95D, let's see where is this D95D locates inside our memory. Okay, so check back from here, the RBP pointer and the buffer address. So we are still executing in the debugger environment. So the debugger environment showing that the RBP, the frame pointer, is located at D960. And now we can see the program crashed at D95D, which is slightly lower than the frame pointer. So now let's check back to the shellcode and see what's the problem here. So this is a unique problem, significantly, especially exclusively for the X86 64-bit shellcode. So only in this scenario you will reach such a problem, and we also have a fix for that. So and this is very interesting regarding how the operating system are operating within the stack. So for example here, let's see from the shellcode line by line, and also let's see how this is, and let's see what happens here. So the first step, the shellcode will going to do a XOR to give the RDX equal to 0. So this is the third argument for the XKV. So we are familiar with that. This is how we're going to create zeros without put a binary 0 in the shellcode. And this does not make any change to the shell, to the stack. However, the second line of the shellcode, push RDX, they were going to push this register into the stack. And where does this register being put into the stack? So when we are returning to our return address, which means that so in the return address, when we are going to return to where the return address locates, which is at D960. So which means that the program will going to consider that everything below D960 does not exist. So this is how the stack manages. So when stack are managing D960, so it will going to start to push the content into the stack starting from this address, which means that the first push of the RDX will going to overwrite the content in the file in the memory address at, let me see, D960. So this is the memory address, and then we are going to make it -8, and we got D958. So now this RDX register was placed at the memory address of D958. And this is not the end, and we can continue. We are going to using this move calculation. So this we're going to store the string, the address of the string, into the RAX register. And this does not change anything in the shell. And then the fourth line, we are going to push the RAX register again into the stack. So what happens here? We're going to minus the address by 8 again, and we got D950. So this comes with the problem. So if you still remember when we are composing the constructing our bat file, so we are placing our shellcode in between the offset of 186 to the offset of 216. So which means that the shellcode is located right below the return address. And because we are running this shellcode, and the shellcode having some push execution, and by doing this, the memory address will going to change. We're going to have some of the overlap with our shellcode. For example, if you check back again on where the program has crashed, the D95D here, this address is higher than D950. Which means that the memory address, which is the command of the shellcode, when the command located between D950 and D958, so this line of shellcode has been corrupted by the shellcode itself. So this is called the shellcode has destroyed itself. So this is a very interesting and very unique problem, only happens on the 64-bit machine, and this will going to give us our insight that how we can change the construction of our the bat file. So what we have to do is that, so you can see, we can first check how large the safe area we have to give to the buffer, to the stack operation. Let's see how many push we have inside this shellcode. So we have 1 RDX, RAX, RDI, and the RDX 1, 2, 3, and 4. So we have 4 push command. So which means that there will be 4 8-byte element being pushed into the stack, and this will take the space of 32 byte, which means that the 32 byte below our return address is not safe to store the shellcode. So this means that we have to make some changes to our shellcode. So in this case, we can no longer set the 186 as our start point, because in this case, the shellcode will locate in between 186 to 216. So we want to give a 32 byte of the buffering area, which is the safe area. So we want to lower the offset of the start as the start of the shellcode. So we can do 186 minus 32, which equals to 156, 54. So let's place this number as the start point of our shellcode. So in this case, the shellcode will be located in 154 to 185, and this will not give the and any value, and also any value lower than 154. For example, if we give it to 144, this will also definitely work. And in this case, ideally, we are going to be able to avoid that problem that the shellcode are destroying itself. So let's have a look. So we first quit. You can see here, we can successfully get our shell. This is a normal shell because again here the stack is running as a child program, as a child process of the debugger, and the debugger is not a setuid program, so we got a normal shell. But this, at least we've proven that with the same return address, right? We didn't change the return address, we just changed the place of our shellcode inside our payload, and this can avoid the problem. So basically here, the next step will be like how we are going to do this in the real environment, which means that we are going to consider the stack, the movement of the stack itself, because we are removing the GDB, the debugger. So again, that's similarly going to give some like a rough guess. So again, we just want to have, for example, we are assuming the debugger are giving you like 160 bytes of the offset or whatever it is, just like give a roughly estimate. So we make it add one. So I love to use 160 bytes because this is like simply can be configured into, for example, 100 in the hex value. So we do D9, D0 and see if it works or not. And now we don't do the debugger, we directly execute L3. And we got segmentation fault. So let's try a relatively larger value. For example, we do what we are here, we previously D9, D0, right? We can do, for example, DA20. Let's see. Well, let's go back to the we may need some of the fine-grained control. So what are the value previously? D9, D0, D9, D0, right? So let's configure. Let's confirm them again. Okay. D9, D0 does not work. D9, D0 does not work. So D890, D990. Okay, so D920 works. So let's just like slightly move the stack. We have to move it low, or we have to move it to a higher address. So which means that, so in this case, previously, right? So previously in the 32-bit machine, so the address will be, when we're moving the address 100 bytes, 120 bytes, 160 bytes higher. But just remember, so that 160 byte is in comparison to the buffer, original buffer size. So in this case, we may not be able to using that large of the offset. So let's try 20 bytes by 20 bytes. All right. So let's try from D940. So every time when you change the value, you have to save the exploit, and then it will going to create you with a new bed file. Oh, D940 works. So let's see. So we're actually having this D940, and then once we have changed the 144 into this as our new shellcode location, we can directly get the root shell. So again, just to give you an idea. So when you are working on that, so in this process, I'm just showing you that there will cause some of the problem if you place the shellcode right below the return address. So when you are working on that, you can change whatever value here, but this is basically based on your calculation. For example, when I was saying like 154 is the safe area, so I select 144 because it's lower than 154. We have a larger safe area between the shellcode and the return address. So you can definitely using your own value. And also for the return addresses, so I just want to show you the idea of how you are going to move your return address, because as of previously I tested on the D920 and it does not work. It caused segmentation fault because it didn't land it into the no-op sled. So here is that. So when you are working on your own machine, so this value will definitely change. So you just want to have a try. For example, when you are exiting, when you quit using the GDB, the debugger, you may want to like change the memory address to a higher address, because in this case the GDB, the debugger will make the stack like more deeper than the normal execution scenario. All right, so now it's time to look for the fourth level. So the fourth level here is actually, in comparison, we're still having the 64-bit program, and the fourth level is that we are going to have only 10 bytes. We only have 10 bytes of the buffer size. And this is a big problem because that with the 10 bytes of the buffer size and with our shellcode for 30 bytes, right? So the 64-bit machine has 30 bytes of the shellcode, which means that the 10-byte buffer cannot hold all of our shellcode. So this means that we cannot copy so we cannot directly jump to the shellcode on our buffer because we cannot hold all of this information. And there is actually also some way to fix that. So this is originally, I think this should be you are going to work on that, but here seems like it seems like to be like a relatively exclusively, it seems to be like relatively difficult. So I'm going to show you some of this idea on how you can work on that. So again, we are going to do the debugging, and now we're going to debug the stack L4. So still we remove the old bad file. And then we got the debugger. So now we get these two addresses. Now the RBP, the frame pointer, are pointing to 960, while the buffer address is 956. So you can easily calculate that now we have only 10 bytes of the buffer. And now this will give us the first idea on what we are going to place our offset, which is we are going to place the return address. So the offset now is 10 plus 8, so the offset will be only 1018. So this is the distance between the buffer and the offset. And then what we are going to change. So we are going to see the idea is that we are going to check back our stack C program, which is our the vulnerable program. And you can see here, so there is actually in between this so ahead of this in addition to the BOF function, which is our vulnerable function, we have another called dummy function. So this dummy function will be very useful in our scenario. It is because that in the dummy function here, we're not going to using this lower dummy function, right? So we're going to having this dummy function. So we first define this dummy function. So the lower one is actually used in between the lower one. So we're actually using this dummy function. Yeah, so we're using this dummy function, and this function is not only being used in the ARM architecture in the macOS, but we also have to use this in our X86 architecture, because this we are going to using it as a bridge, as a proxy to store our vulnerable string. So let's see how it works. So in the main function now, so previously when we are working on that, so we can use dummy function, or we can directly using the BOF function here. So this is in the textbook, in the lecture, we are directly using this BOF function, so using that to call that function, right? So we directly call the vulnerable function. However, here we're adding one other layer of this proxy. So we first call the dummy function and pass the string to the dummy function. And then inside the dummy function, dummy function has taken the string as their argument, and this string will be then passed to the BOF, which is our vulnerable function. So this gives us an idea. So although we have a relatively small, very, very small size for our vulnerable function, which is 10 bytes, but here, when we are calling the dummy function, there is still, this string has been stored inside the dummy function stack. So we can have a way to check where these dummy functions string are located in the program, because we are still executing on it. So let's directly using the P, and when we tap the str, when we tap the string here, it will give you a address. So this address is very important. And you can see here the DD90. So this is a relatively higher address than the buffer inside your BOF in your vulnerable function. So let's see how much higher it is, right? 43A, so this equals to 1082 bytes. You can see this is a relatively higher address comparing with your vulnerable function. So it means that in this case, we are not going to jump to the vulnerable function. We're not going to jump to the shellcode inside our vulnerable function because we cannot hold that much data. So the idea is that we are going to jump to another string, which can be stored completely inside the memory, inside the stack. So now we are going to jump to this string. So this is our idea. So basically here, what we have to change. So first, everything is still like this. We do not change the place of the shellcode because we are still going to have the problem that shellcode will going to destroy itself if placed too close to the return address, and we do not. And the offset has been changed. So the only thing we have to change is changing this return address. So now it becomes very simple. So we are going to return to the string inside this string function. So let's do directly do dd90. And we have to add some of the offset. For example, we directly add the offset of 160. So remember, this is because you're going to run it outside this GNU debugger. So we have to make it higher. All right. So because 160 is already higher than the starter code, but since we are outside of this debugger, we can make it higher. So let's see if it works. I have to store it first, and then yeah, we got it directly. So which means that here, so you can see here when we're placing this one, we're using I can actually using, for example, using this like a calculation formula here, or I can also using DE90. So this will be the same. And yeah, so this will be the introduction for the all four levels of this shellcode on the X86 architecture. And I just want to give you some of the idea. So basically, this is actually one of the four most difficult, especially for the task 5 and 6 on the 64-bit machine. So this is extremely difficult. And when you are working on the program, when you are working on your own lab, so I suggest you having having the paper and pen on hand, and you can really draw the stack diagram, just like I have done in the class. So you can draw the stack diagram clearly, and you are going to having a better understanding on how the stack works. For example, how the stack will shrink after when adding the GNU debugger, and how this no-op sled works, and how the no-op sled will guide into the return address. So all of these details you will be able to learn when you are really working on this task 5 and 6. So I'm not going to introduce task 7 and 8. All of these incoming countermeasures related are not that hard. So basically, I hope you can work on that by yourself. So basically, after you have finished watching this video, I think you will be able to get some clear idea on how this task 3 to 6 really works in the X86 machine. All right, and for the ARM machine, for the MacOS machine, I'm going to using another video to introduce to it. Okay, and that will be the introduction for the lab 2, our buffer overflow lab on the X86 architecture.